Okay, we're here for some practice on how to use the visualization method instead of using a formula, and long may it be helpful. Let's get going. So we want to first of all realize that we can't simplify that function any further, and there's a very clear multiplication in between there. So we're going to be picking the it's actually a very interesting one here. Now, I would say ordinarily we would be picking the x4 to differentiate, but knowing that this will reduce over 4 iterations, I'm actually going to go for this. Sometimes it's like it's a choice between what you can differentiate and what you can't. Technically, you're not allowed, or you're not expected to integrate ln, right? It's like, well, what's that? You can do that. You can see it as 1 times ln x and do it by parts, right? But there are some functions you stick away from. With differentiation, this is perfectly fine. So I'm going to pick my u as that, and then v is x4, not v, but v dashed, because that's a derivative. So those are the 2 elements up there. I've got my v dashed multiplied by u. And as you know, that could be either way around, right? So I could rewrite this question as ln x x4, probably put dot there, dx. And that's really the same thing. So let's not get too particular about which way around they are. And the next thing we want is to find the derivative in the cases where we have or have not. So that's 1 over x. And then we have the derivative here, so we want to antiderivative. That means we get integrate, so that's going to become 5 over 5. Okay. So we've done the hard bit. We've decided what we're going to integrate and differentiate. We put it into our organized little table, which is already making the page look beautiful. So we're first of all going to apply our method, and our method says that when we're integrating by parts, we first of all go down in this motion. So that's a multiplication. So if it's not clear, we are, where should we put this? We'll just put it here. This represents our uv, the start, the first multiplication. I'm going to put the 5th x5 first with ln x second, and we're going to take away the integral of the bottom 2. So we've got that arrow there. So that's going to go in as quite cool. I mean, I'm going to simplify it first. So we've got 1 over x and x. So that's going to cancel to become x to the power 4. And that 5th, if you'll forgive me, is going to come out the front. So I'll do a couple of things at once there. It's actually rather good there that it's reduced. It's reduced so that it's a single function. We can then integrate that as usual, and that's the end of business. So we'll end up with x to the 5 times a 5th. Okay, I'll just put that there. That's the integral, but we've got to multiply that by a 5th again. So that's 1 over 25 plus c. So let's try it for another one. We can confirm that these cannot be simplified any further. And we're going to choose, because e to the x is for sure going to be a pain to reduce. So it's going to have to be the 2x to reduce. U dashed is 2, and then there'll be an antiderivative that's going to be integrating. It's the same. So it doesn't really matter what it is. The first e is so nice. And the second e has gone awry, shall we say. Okay, remembering our method, we're going to go across here. These are the 2 that are going to multiply first. We've got 2x e to the x. I did say in another video that it's actually worth writing the question again. So, I mean, why don't we write it right next to it? Yeah, so there we are. And we're then going to go across. So we're going to take away integral of these bottom 2 things. So if it's a 2 e to the x, I'm going to think in my head first. Let's write the 2 on the outside and have e to the x on the inside on its own. This is what we call, let's pop quiz, what do we call it? Yeah, so we call it an integrating factor. All right, this is going to come out, and then we need to integrate for the last time. It's just going to stay the same, which is really good. E to the x doesn't do anything with its life. Plus c. La-da! And yes, there are some more simple factorizing to occur here, and I feel that it wouldn't take too long to just actually do it. So 2 in the e to the x come out, and that's 2 to the e to the x. So pretty nice factor there. All right, last one. Why did I put this here? I put this here because, well, I wanted at least 3, but aside, this looks a bit odd, right? This might be coming up in an exam, might be the one that makes you think twice about whether you actually know it or not, right? So I'm just not going to panic. I think that's the most important thing. The first thing is x plus 1 is great, but this needs to be seen as this. So first of all, changing that question. Now considering what would I integrate and what would I differentiate, right? So I could do both. If I differentiate something to the power of a half, then the half goes down and it becomes minus the half at the index. If I integrate such a thing, then I plus 1, which is 3 over 2, and then multiply by 2/3. It's not, there's not any taboos here, so that's fine. Which one to pick? If we're looking ahead, which one I would prefer to integrate was the x plus 1. Well, I know that x plus 2 to the half is sort of trapped inside that square root. Okay, that's like a lock, which maybe we don't appreciate right now, but it's locked in there, and so it's less likely to cancel. And if we integrate it, it's still locked because the fractional index. So let's choose to at least reduce one of them, and that would be the x plus 1. I'm hoping that will reduce. So we're going to choose this one as u and this one as v dashed. And we're going to start our table, x plus 1, and v dashed that's probably the best way to have it, this format. U dashed is equal to 1. That's brilliant. That's the best we can hope for. The antiderivative. So when we're coming up this way, what we're doing is integrating. And that means that we want to be integrating using a method. And if we want to be very careful, we can use a chain rule. So we can say u is x plus 2 and y equals u to the half. Obviously, if we find the derivative of that is 1, keeping up our good habits and saying, yeah, but it's 1 over 1 that we want, which is still 1, but we've got the good habit. Integrate y, which is u to the 3 over 2 now. That's 1.5. Divided by that, in other words, multiply by a reciprocal, which is 2/3. And then we're going to multiply across because it's a chain rule. So that's 2/3 x plus 2, 3 over 2. Now I'm not going to put plus c yet because this is only a secondary. This is an off part of the methodology. The final one's not quite done yet. What we found is the answer to integrating here. We're going to put that in, 2/3 x plus 2, 3 over 2. Okay, so let's clear up some space. We're now looking to do the methodology of visualization. Not the nicest. Probably going to have to be very careful here. 2/3 x plus 1, x plus 2, 3 over 2. That little bit's going to make all the difference. Now subtract the integral of, what was it, these two elements here? Oh, that's really good because one of them is 1. The 2/3 is an integrating factor, and that's going to go behind the integrand. So I'm going to take that out straight away, and I've got x plus 2 to the 3 over 2 dx. So my last move in order to sort this as a question is to move some bits around. So bear with me. I've done an integration where we used some form of the chain rule for integration. We do the same again. So u equals x plus 2 and y equals, for the sake of argument, we'll just call it y. U is 3 over 2. And then we're looking for u dashed, which is 1. And that's just going to be our good habits that take us to this place. And integral of y, which is now 5 over 2 u, and multiplied by 2/5. And so that's going to multiply in. The 2/5 is going to multiply by the 2/3 to give 4 over 15. And then we must remember that u is x plus 2, and it has a new power, 5 over 2, and it has a plus c. Okay, so that's taking it through to the finality and possibly some factorizing to do, but we're going to leave it there and go for a challenge question. These challenge questions are super useful because they're actually designed to mess you about. If they do ever come up, you'll notice them because the function that's supposed to reduce, it doesn't. See there that the function itself won't reduce in the first instance anyway. It will take a couple. And you have over here a cycling or a cyclic function that just won't ever reduce. So in this case, we need to be aware that we're going to need to be extra organized. So let's take us through the methodology. Definitely going to start reducing x squared to x, and then v dash being cosine x. So if we think about what this is going to be, we're just going to go to a nice positive sine x. All right, now we're going to use our method. I could do it all in one, if that's okay. I do an arrow, and then I do another arrow like that straight away. And so we can write it all out. X squared cosine x dx. Right, now this is where we have to be very careful with the layout. So uv, so that's x squared sine x subtract the integral of x sine x. Look where we are. We're back roughly where we started. You've got a trigonometric function. It's basically just a cyclic to me. But the x squared has been reduced to x to the 1, right? X. So we made progress. In order to get this next bit, we need to use integration by parts, because you see we've got a multiplication of 2 that can't be made smaller. So now, instead of u equals x squared, you noticed we're down again. That's 1. V dashed in this case is sine x. And then when we're going to be integrating sine x, it's going to go to negative cosine x. And using our methodology, imagine having to do twice in the exam. Not bad, really, when you have this method, I think. Let's realize what we're finding. We're finding this at this point. So if we're going to write this again, whatever result we get is going to go into that box. So the result from that is going to be u times x, so negative x cosine x. And we're going to be subtracting, because remember this is integration by parts, and it feels like we've already done this bit, but we're going to be subtracting the integral of this times this, which just so happens to be that negative is going to come out the front to make it positive, and that's going to go in there fairly nicely, I would say. If we just work that to its finality, we've got negative x cosine x, and if we integrate cosine, we get sine, so plus sine x plus c. What have we found? We've found the result of the blue box. We're going to continue the question down here. The x squared sine x remains the same, always will. But what we have now is a subtraction of this expression. So that's going to be plus x cos x, subtract sine x, and plus c. I know you feel like it should be take away c, but you can add a negative number. Right, so that plus c stays plus. In order to sort the second part of the method out, we needed to employ a second round of integration by parts. You can see the first and the second here, they're kind of making things fairly organized. But you'll also notice that when I did the working out here, it's nothing like it's kept in line, okay? So all it being in line is also as important as the actual method, right? Once you've found that, it goes back in just like in the old bracket system. Okay, I hope you enjoyed working through these problems. They are one of the hardest things you're going to be doing at this level, but really worth it. And let me know if you want to see more, if you want some more practice on this, anything at all. Be great to hear from you. Take care and keep chin up, working hard this year. It's worth it, I promise. Don't give up. If you want to support this channel, head on over to Patreon. You can get extra resources and a free gift with every sub.